Good morning, good afternoon. My name is Giulio Ruffini, and I am the Neuroelectrics CTO, CSO. I'm here to give you a talk about model-driven tES, what we call tES 3.0. So, as disclosures, I am the CTO of Neuroelectrics, a medical device company based in Barcelona and also in the US, producing brain stimulation devices. Our focus is personalized computational brain therapy, and this is the driver of the work I do and the driver of my research team. We aim to provide personalized brain therapy by measuring and modifying brain function to maximize brain health. And we work with different types of pathologies and thinking about all the patients that are out there and who need solutions. And in particular, we work on epilepsy, Alzheimer's disease, and in depression. So first, briefly, what is tES? tES is a non-invasive neuromodulatory technique. By this, I mean that it's a sub-threshold technique. It doesn't by itself cause neurons to fire like other ones, like TMS. And as a summary, I would say it's a persistent mesoscale, weak electric field action at low frequencies. This is done by passing small currents to the scalp to generate fairly uniform electric fields without a very high resolution, indeed, that alter membrane potential, mostly in pyramidal cells, modifying dynamics, and this leads to plastic effects. Normally, this is applied in 20 to 60-minute sessions, multiple sessions to achieve plastic effects for therapy. And the most common form is TDCS, but also TACS and TRNS are also used. It's extremely safe. It has an excellent safety track record. Indeed, the power delivered by a device is much, much less than that of a mobile phone when you apply it to your ear. So the question that we have ahead of us is, it's a powerful technique, and we have developed Neuroelectrics and other places, devices that can deliver multifocal stimulation, applying currents in multiple places in the brain and with multiple waveforms. And the question is, how can we use this? How can we improve the efficacy of the application? And as usual, as a physicist background, I will tell you that you need a good model of reality in order to improve your models and control things better. So this leads us to the concept of Neurotwin, which is a concept we're developing in Neuroelectrics. And I know that other people are developing similar things, which is basically to develop digital twins of the human brain, right? So what is a neurotwin? By this, we mean a personalized model of a brain of the head, in particular of a patient. And it's a compressed computational rendition of reality of this patient's brain with sufficient detail to optimize brain stimulation protocols, and in the context of a specific pathology and for a specific patient. So, and this is achieved using multi-scale approach and multiple levels of abstraction in the modeling framework, because the brain is a very complex system, right? So we have different modeling layers in what we do. One is the physical layer, so modeling the electric fields that are generated by our systems, by brain stimulation, and also the electric fields that the brain generates itself. This is the physics part. And then there's the physiological layer that is necessary to understand the dynamics of the brain, the computational aspects of the brain, pathological aspects of the brain in the physiological sense. So for this, we use neural mass models and brain networks of such neural mass models. And then we also use an abstract layer, which is useful oftentimes, which is a very basic rendition of some aspects of how the brain works in order to understand, to ask fundamental questions about things like criticality, things about transitions between different states, and just to get a better understanding of what's going on, and perhaps get some ideas on how to stimulate the brain. So this involves models like the Ising model, which I will briefly mention, or a Hopf model, as opposed to the more complex neural mass models, and indeed at the microscale neuron compartmental neuron models, right? So what are the requirements for tES optimization? You need a realistic rendition of the physical models of the electric field in the brain, and then you need appropriate models for the physiology. And this includes physiopathology and models for interaction of the electric fields that we generate and we model with neurons, and at the population level at least, and plasticity, modeling, models of plasticity. So we also need, of course, a definition of what is healthy, what is a healthy state of the brain, and with that definition, try to apply stimulation in order to reach that state. And what I will be talking about here started some years ago into projects, which I would refer to as tES 2.0, which are high and luminous. These were European projects funded by the Future and Emerging Technologies program that we have been very fortunate to be supported by. And in this, we started developing the first models of interaction. So how does an electric field affect neurons? And we understood that mostly this affects pyramidal cells, and the effect is important because pyramidal cells are very aligned, and you end up with an enhancement of effect from this homogeneous stimulation of a bunch of neurons. We came up with a model, the first models for the interaction. We call it the lambda E model at the time, basically saying that the effect of the field can be excitatory, inhibitory to the extent that the component of the electric field parallel to the long neuron is acting, right? And we also learned by looking at literature that their networks of neurons can be very, very sensitive. And we actually expanded, and we thought, well, if tDCS or tACS can affect brain dynamics and they generate these weak electric fields, how big are these fields compared to the fields that the brain itself generates when it operates, right? Because if it's so sensitive, maybe that plays a role too. And we analyzed this in this paper here, realistic model of mesoscopic haptic coupling in the human brain. And we essentially show there through computational models that the electric fields of the self-generated electric fields in the human brain are of comparable size to those of our tES, tDCS brain stimulation, which is very interesting and something that we need to explore more, I think. But the message here is that, okay, even though individual neurons are not that sensitive to the electric fields, you can induce like 0.1 millivolt membrane potential perturbations. When you couple a lot of them, this leads to network phenomena that we need to understand better. We also developed techniques for creating realistic models of electric fields in the brain. This was work that was started in the HIVE project by Pedro Miranda, and we now have pipelines to use this quite regularly. It's also important to emphasize that personalization of electric fields is important because there is quite a bit of variability in the electric field you generate in a patient's brain if you don't take into account their anatomy. So if you don't adjust the currents and locations of electrodes, you end up with that variability in the electric fields that you generate, and this can be a confound in the context of clinical studies, but also, of course, in the context of therapy. So this points to the need of being important to actually model this carefully, right? And as I mentioned, we have now a pipeline in place that we use in our clinical studies, and for people who are interested in doing some studies themselves, to start from the MRI of a patient, extract the tissues, segment them, create a finite element model, and then using algorithms that we developed almost 10 years ago now. The Stimweaver algorithm, we can actually optimize now the locations of electrodes to hit that target. By target here, I should clarify that we mean a specification of the desired electric field in the cortical surface, and that this specification is weighted. We have begun some years ago now the application of these ideas in the context of epilepsy, and the first one was an open label study that we did in collaboration with Beth Israel, Boston Children's, and Instituto Nacional de Neurología y Neurocirugía, where we applied targeted stimulation to patients based on their specific targets. And this study involved 20 patients, of which 17 completed the protocol. And we saw a reduction of 47% in the seizure frequency rate of these patients and almost a 50% responder rate. And so the results were very encouraging. And these results have been replicated in similar studies now with our colleagues in Marseille. So let me talk a little bit now about physiology. So we entered the field now of tES 3.0. And up to now, what I've been talking about is using physical neurotwins in order to do optimized stimulation. But here I want to tell you about what we're doing now in physiology. So expanding this to the physiology part. So this is part of two projects. The first one is called Neurotwin, and this is funded by the European Commission and in collaboration with other partners that we'll mention shortly. The motivation is to study how to treat patients with Alzheimer's disease, which is a neuropsychiatric disorder with a lot of burden and with many people affected all over the world, right? So the vision, again, is that the brain is a dynamical network and each brain is different. And we would like to personalize treatment for these patients or understand at least what are the mechanisms by which we can stimulate. So the goal is to develop whole brain models that predict the physiological effects of transcranial automatic stimulation and design optimal stimulations for AD. As I mentioned, we have many collaborators here that I would like to briefly mention, including Michael Nish, Gustavo Deco, Giacomo Koch, Indiano Santarecki, Javier Marquez, etc. The other project in which we're doing this Neurotwin approach is called Galvania. This is an ERC synergy project. So this is funded by the European Research Council and with my collaborators, Fabrice Wendling, who works on computational modeling, and we have been collaborating with him many years, and Fabrice Bartolomei, who is a neurologist, epileptologist, and who is helping with all the clinical perspective of the situation of the problem. And the approach in Galvani is, as I mentioned before, and it's in Neurotwin, which is a multi-scale study of to try to construct these models from subcellular to micromicroscopic to macroscopic modeling. The process of creating neurotwins at the high level involves collecting patient data, which may vary depending on the pathology and situation. But for example, in Alzheimer's, it involves fMRI, DMRI, EEG, anatomical MRI, PET, etc. Or in the context of epilepsy, includes SEEG, for example. And with this data, we construct the Neurotwin model for the patient, which includes these neural mass models, which are embedded in parcels in the brain and connected with the patient's connectome derived from diffusion weighted MRI. And then once this Neurotwin is in place, we can apply in silico stimulation and find out what is the best stimulation for the patient with a specific target in mind, which, for example, in epilepsy is to reduce seizures or the spread of seizures. And in the case of Alzheimer's, would be to, for example, increase gamma power in the prefrontal cortex. Yeah, and this is described in some papers that I have linked below. One is an older one in which we put some of the main ideas, what we wanted to do, and the other one is more of a perspective paper on the use of networks to optimize stimulation. At the microscale level, one of the things that we need to understand better is, okay, even if we are talking about a single neuron, can we justify the use of this lambda E model, which basically says that the degree of excitation or inhibition is proportional to the dot product, the vector product, dot product between the axis, the main axis of the neuron and the electric field. And for this, we followed work that Aberra did already in 2018 in constructing compartment neuron models using neuron, and then deriving from that their characteristics, so their polarization in different regions of the neuron as a response to the electrical stimulation. So what we saw with this, one of the main takeaways is that for the most part, little error is included. It's incurred if you just stick to the lambda E approach. So this dot product accounts for most of the variance in the response of the electric of the membrane polarization of the neurons to the electric field. Although we use a spherical harmonics decomposition, and you can also see some tinier effects in higher order harmonics. So this was one of the main takeaways, but of course now we have models for each single neuron to understand how they respond. And we also saw that some interneurons, not only pyramidal cells, can couple relatively strongly to the electric fields. And in fact, other pyramidal cells have the opposite response than the standard ones that we think about because of their orientation. The mesoscale level, what we have been endeavoring developing neuromass models for epilepsy and Alzheimer's. In both cases, we developed something called the laminar neuromass model. Started this work in 2018. And the idea here is to expand the formalism of neuromass models, which describes the behavior of populations of cells, by embedding them in a physical medium and giving them geometrical properties like length and things like that, so that we can actually predict from them with a physical basis things like the SEG data they generate, the EEG data they generate, and things like that. We also have a bold model on top of the neuromass model that we have applied. And in the case of epilepsy, we went beyond that and we added a model for the dynamics of chlorine accumulation for the cycle of chlorine intake and outtake in the cell, and to describe something that we believe is a mechanism for initiation for the pathology in epilepsy, which is the depolarizing GABA. And using this model, we show that one can actually reproduce quite accurately the choreography of a seizure, starting from the preictal to the fast onset to the ictal phase. And this is described in this paper led by Dr. López Solá. In order to model the SEG in particular, EG is a bit easier, but for SEG, you actually have to have a physical model of how the currents that are generated at synapses actually affect the entire neuron, how the neurons, the return currents in neurons, how they are generated, and how this maps out into SEG. And this was very nice work led by Borja, one of other people in my team, that analyzed this problem and provided some models based again on compartment models to give us this kind of linear transformation. At the end, it's a linear transformation between synaptic activity and the measurement of SEG, which you can then translate into CSD and other things like that. So this is one of the tools that we actually needed to make a closer link with the measurements from SEG in epilepsy, right? And in a similar vein, in work led by José Sánchez Todo, we investigated, we deployed the laminar model in order to reproduce macaque monkey measurements with multi-probes. And we show that with this model, we can reproduce the deep and superficial distribution of fast and slow power generated by the cells. And we also actually studied how these models respond to stimulation, which is something that we are very interested in the context of Alzheimer's, because in the context of Alzheimer's, we are investigating the use of tES. And these models predict, once you add the electromagnetic coupling, they predict how the system responds to a specific stimulation with a given amplitude and frequency. And you can see the emergence of the so-called Arnold tones in these models very nicely. So in the context of Alzheimer's disease, one of the first things that we needed in order to construct a model, computational models for these pathologies, we need to understand, to have a model of pathology. And because if we understand the mechanistic aspects of pathology, then we can map them in a reasonable way, in a principled way, into the neuromass model. So this is one part of the work that we have been doing, and it's part of a manuscript in preparation, where we trace out the causes and the path of Alzheimer's based on the literature, starting from inflammation, which may be due to prior infection or pollution, in combination with genetic susceptibilities, And into what we understand is the release of beta-amyloid oligomers that lead to a hyperexcitability. And in a vicious circle, this leads to PV cell failure, and with a subsequent cascade of events that you can map out also in terms of things you can measure, like EEG or PET or fMRI bolt. We are showing, we will essentially show that you can actually map pathology into phenomena like decrease of gamma power, the prodromal stages, slowing of EEG, and then to a general power decrease as the circuits are more damaged. And similarly, in terms of fMRI bolt, what type of phenomena you would observe more at the macro scale, how this can also lead to seizures and cognitive impairment. So this is part of the work that we have been doing in Neurotwin. For Alzheimer's, as I mentioned, we are interested in, we think that stimulating at gamma band frequencies is a potential way to try to recover these damaged fast circuits in the brain. One of the trademarks of Alzheimer's is the slowing of EEG. The slowing, especially in low frequencies, you have an increase of power and a decrease of gamma power that can be better observed with TMS EEG, as my colleagues at Fondazione Santa Lucia, Giacomo Koch, and collaborators have shown. Based on some research work that was done at Itzai's lab, showing that stimulating gamma frequency may be a way to recover the circuits, we are now organizing a clinical study that is ongoing with Alzheimer's patients with stimulation at 40 Hertz in a specific set of regions in the brain for our patients. So at the macroscale level, well, one might wonder why is it necessary to model a macroscale. I mean, the case of Alzheimer's makes it quite clear that you need to model the whole brain. The brain is a connected network, even if it's not affected globally. There are connections, and you may have indirect or direct desired or undesired effects from stimulation. So whether we like it or not, with tES, we are also affecting relatively large regions of the cortex, even if we use focal montages because of the physics of the problem, right? So you need to think of the cortex at the mesoscale and macroscale. And yeah, this is work that we, as I mentioned, we started doing already some years ago. It's paper by Jose, this preprint by Jose, and the idea is to, for example, in galvanic, in the context of epilepsy, develop models for a seizure network, but then embed this seizure network in the whole brain, and in this way connect the pathology and the dynamics as detected by SEG to global phenomena like SEG or even fMRI bolt. And anyways, once these models are in place, you can start doing simulations of pathology. As I mentioned before, we have some mechanistic ideas on what pathology affects in Alzheimer's or in epilepsy, and you can simulate those in the models and then apply stimulation to reduce or to bring the dynamics into a state which is closer to you. In the case of Alzheimer's, we are working with multiple data sources, and we have been developing tools to simulate both EEG and PET and fMRI into the model of the patient in order to understand what the pathology is in terms of its biomarkers and dynamical traits and how to stimulate it. And as I mentioned, we're using different modeling schemes for this. In the context of Galvani, this ERC project, the process is similar. So we start with a research track focusing on the concept of what models we want to use, what are the mechanisms that we want to include, the biophysics and all that, and then develop methods for patient-specific optimization, personalization optimization, and all this is translated into a clinical track. In the next 6 months, we'll be beginning the clinical study in the context of Galvani with epilepsy patients in a multi-study center. And here the concept is to identify seizure networks with SEEG and other data, EEG and semiology, and construct models for the epileptogenic network in the context of the whole brain. And for each patient, then decide what is the best way to limit the impact of the pathology. And this has two sides. Well, one of them is, can we reduce the probability of seizures? And even if we cannot do that, can we reduce the probability of spread of seizures? And these are the two things that we're investigating right now. So as a summary, I would say that going from tES 1.0 to 3.0, we have gone from the world of sponges to small electrodes, from target definition that has been based on 1020 system and some principles and science principles, to targets which are parcels defined by the neurologist. And with that, we have constructed a physics-based target. In tES 3.0, this changes because we now not only have a model of the brain and of the physiology, but we also have to define a target in physiological language. So the target is no longer, I want an electric field here because I want to excite or inhibit this area, but perhaps I want to reduce the probability of seizures, or I want to increase gamma power in the prefrontal cortex, right? So these are different loss functions that have to use in the optimization methods. And to close, I just want to say, again, to summarize that using multi-channel montages with small electrodes offer the opportunity for more precise, meaningful stimulation, both single targets or brain networks. The physical aspect, the physics aspect of optimization and personalization. So the physical neurotwins are now operational in our clinical trials, and we also do this for interested researchers. We have preliminary data from earlier work from my colleagues at the ADMC that tES may be useful for AD, and also from sensory stimulation studies. And we are developing this technology and applying it into AD and epilepsy for this hybrid modeling, as we call it, that is now being translated into 2 clinical trials. One of them already started in the context of Neurotwin for epilepsy patients, and the one for Alzheimer's, which will begin shortly, and both of them should be closing by the end of 25. Thank you very much for your attention. And to close, I just want to leave you here with a slide of papers that I've been mentioning in case you want to take a closer look. Thank my team, which includes the operations team and people working in deep learning applications, and also the researchers more closer to the Neurotwin concept. And my collaborators, which I am very fortunate to have quite a few and very good ones. Thank you very much for your attention and for your time.